All right, so we've been working a lot with logs, and all of the logs that we've had have different bases. We've had base 2, base 3, all sorts of different things. So we're going to be doing two big things. We're going to be focusing, first of all, on the common log, and then we're going to move and do what we call a change of base formula. So the common log is just one specific type of log. It's just log base 10. So common log, we write this as y equals log base 10 of x. So depending on how advanced your calculator is, some calculators only have the common log. So like if you have your iPhone, for instance, you turn it sideways, add a whole bunch of commands over on the left-hand side. If you see the word log, that log command only does the common log. Our calculators are now more advanced, so we can do any log, but back in the day, we only had just the common log, and it's so common, in fact, that they literally just write it as log. So if you ever see a log without a base written, you can assume that it's base 10. Any other base would have to be written down there. All right, so what that represents, remember, is the power on 10 that would give us whatever x is. So these, we can plug them into our calculator, and I'm going to show you how we would do that. And like I said, you could actually use your iPhone for these as well. So this log 6, what we're going to do is this button is right down, like here's the 1, then there's 10 to the x, and the blue key above that is the log button. So we are going to hit Control first, then that button, and then we're just going to skip over the log. We don't need to write the base in, because if we don't type anything in, our calculator will assume we mean 10. So we're just going to type 6 in here. So this would be the power on 10 that would give us an answer of 6. So hit enter. Always give me 3 decimal places. Let's go with 3. So this would be 0.778. Okay, so this would be 0.778. That means if I raise 10 to this power, I'm going to get 6, which should make sense, because 10 to the first would give me 10, and since 6 is smaller than 10, my power would be smaller than 1. So make sure you're thinking logically about these. Let's do another one. Hit that log button first. You can skip right over the base. Your calculator will assume it's 10. Hit enter. That's going to be a negative value, which again, that should make sense. Remember, negative exponents give us fractions or decimals. So this decimal, we would take a negative exponent in order to come up with that. All right, so again, 3 decimals, that would be negative 0.456. The 5 would round up. So for those first couple problems, you basically just need to know how to use your calculator. So here's a couple things that I want you guys to basically have memorized. Remember, a log just represents an exponent. So with the common log, it would be an exponent that we put on 10. So if we have like this, for instance, if we have log of x equals y, if we know that, what that means is that 10 to the power of y gives me x. So if I'm trying to find log of x, it means 10 to what power gives me x. So couple of common ones that you should know. Log of 1. Okay, that means 10 to what power gives me an answer of 1, and that would be a power of 0. So remember, this is basically saying 10 to the 0 equals 1, which hopefully we know to be true. Another one, we could say that log of 10, that means 10 to what power gives me 10, and that would be 10 to the first power. So again, what that means is just 10 to the first gives me 10. So if you see either one of those, log of 1, just know it's 0, and log of 10, know it's 1. Those could pop up here and there. So this little statement just here, we use common logs in different sciences and engineering. 2 of their most common applications are in sound measurements, like decimals, and then the magnitude of earthquakes. I'm sure you guys have heard of the Richter scale before. Those both use common logs. So this example 2, we're going to talk about decimals, loudness of sound. So this is a formula that is actually used to measure decibels, different different intensities that the human ear can hear. So we've got I stands for the intensity of the sound, and M is the minimum intensity. So since we're looking in this problem for kind of a comparison between intensity and minimum intensity, we are just going to say that we are going to let M equal 1. So just the number 1, and that we can do a comparison. So detectable by the human ear says the sound of a jet engine can reach a loudness of, that's supposed to be 125, that slash snuck in there. So 125 decibels. So we're trying to see how much louder that is than the minimal intensity of an audible sound. Okay, so like I said, we're just going to use a 1 as our minimal decimal, and we'll be able to see how many times that our intensity ends up being. So our loudness, we're going to use this formula right here. The loudness, it says, is 125 decibels, so we can type that in for L. 10 times the log of, we don't know what I is, that's what we're trying to solve for, and then we're just treating M as 1. So this would just be 10 times the log of just I, because I divided by 1 would just be I. So we're going to solve this for I. So in order to do that, we need to get the variable by itself. So we will start by dividing both sides by 10. So the 10s will cancel here. And if I divide this by 10, I will get 12.5. Remember the trick where I can just move my decimal over one place. And then this is now log of I. So remember from your previous section, if you've got log functions and you're trying to solve for something, the easiest way to do that is to just put it back in exponential form. And remember, this base is 10. So I would write 10 to the 12.5 power is equal to I. So now I have I by itself, and I actually can answer the question. So what that means is that I have 10 to the 12.5 power. So that ends up being just a gigantic number. If you were to plug this into your calculator, it ends up being about 3 trillion. Many, many, many zeros. That's 12 zeros. So this is my answer. It is this much times the minimum intensity. So that's a very, very loud decibel. Okay, so just kind of an application that you can use. So this sentence right here is going to apply to the next page. So if both sides can't be written as powers of the same base, which that's like your 7-2 stuff we saw, so you can solve by taking the log of each side. So in case you don't know what I'm talking about at all, example 3. So this one, I have 5 to the x equals 62. One of the previous sections that we saw, if this were like a 25 or like a 125, we could nice and easily like write it as a power of 5, but 62 is not a known power of 5, so we have to use an alternate method. And what we do is we're going to take the log of each side of that equation. Okay, so we start by taking the log of both sides. And when we say take the log, we mean take the common log. So this is how we're going to start these problems off for both the equations and the inequalities. So start by taking the log of the lefts, and we have 5 to the x, and then take the log of the right. That's just the log of 62. So next what we do is we start to apply these properties that we learned in the previous section. And we have this property that says if I have an exponent inside of my natural log function, I can move it out front as a coefficient. All right, so that's what I'm going to do. So I'm going to have x times log of 5. So remember, log of 5 is just a number. I could figure out what that decimal value is by plugging it into the calculator. And then same thing with log of 62. So in order to solve for x, what I'm going to do is divide by this. So divide both sides by the log of 5. Okay, so this number would cancel. I'll have just x on the left-hand side, and then I'll have to use my calculator to get this number. All right, so it would look like this. So when I type these in, I'm going to set up a little fraction so I can hit control and then the division sign. So I'm going to type the log of, skip the base, 62, over the log of, skip the base again, 5. So I would hit enter, and I get this. So give me 3 decimal places. The nearest, or I'm sorry, 10 thousandths would be 4 decimal places. So 2 point, and then give me 4 decimal places, so 5, 6, 4, 3. So remember what this represents, this is the power on 5 that would give me an answer of 62. And hopefully this number makes sense, because if I raise 5 to the second power, it would give me 25. If I raise 5 to the third power, it would give me 125. So since 62 is somewhere between 25 and 125, my power should be somewhere between 2 and 3. So like I said, hopefully that makes sense. This one we're going to do the same thing. 3 and 2 have different bases, so we're not going to get anywhere by trying to convert them. So what we do is we again take the log of both sides. Okay, so what we do with these things is the same as we did up in the previous problem. We now have a property that says that this exponent can come out front and this exponent can come out front. These ones are going to be a little bit trickier because I have an exponent in 2 places, but I'll walk you through it. So the 7x comes out front, and that's kind of like a coefficient in front of the log of 3. And remember, log of 3 is just going to be a number. Greater than, and this 5x minus 2 will come out front as a coefficient times the log of 2. Okay, so here's where things get a little bit tricky because I'm trying to get the x by itself. But as of right now, I have an x in 2 different places. So over on this side, I actually end up distributing the log of 2 to both of these pieces. So this is 7x times the log of 3 greater than, I'm going to distribute that log of 2. So I have 5x times the log of 2 and then minus 2 times the log of 2. All right, so next step, what I have to do is I need to get my x's together. So I have two different pieces that have x's. I want to get these both on one side of the equation. So I'm going to take this term and I'm going to subtract it over here. All right, so I'll have 7x times the log of 3 minus 5x times the log of 2 is greater than, and then I'm still going to have this thing on the right-hand side. Okay, so we are getting there. Next thing I need to do is take these x's and factor them out because I need to just have a single x. So I'm going to factor out this x, and then in parentheses I'll have 7 times the log of 3, which is just a number, minus 5 times the log of 2. And I am just one step away. So the last thing I do is I'm going to divide both sides by this whole giant thing in parentheses. And once I do that, then I'll get the x by itself. Okay, so two things when I go to plug this in. Here's the first thing that I need to know. I need to know if this thing that I just divided by is negative, because remember, if I divide by a negative, I have to flip the sign. So it's very important that I know. So I'm going to plug that whole thing in. So 7 times the log of 3 minus 5 times the log of 2. Okay, it wasn't negative, so that means I don't have to change the sign. So I'm going to take this numerator, I'm going to take negative 2 times the log of 2, and I'm going to divide it by, now I'm just going to copy and paste this, so I don't have to retype that whole thing again. All right, so I get this. So I get x is greater than, this is negative 0. Remember 10 thousandths again, so that means 4 decimal places. And that 1 would round up because of the 5. So that is your final answer. These are really tricky. We'll make sure we go over some of those together. All right, last quick little thing here is something called the change of base formula. So our change of base formula, like I said, it was really applicable back in the good old days when our calculators weren't so fancy, because it used to be literally that every single calculator could only do the common log. So we had this formula that could change from any other base into log base 10. So it goes like this. So if I had log base a of n, that would come out to equal log of n, so common log of n, and then divided by common log of a. All right, so this works out very nicely. There is actually a proof in the book, so I was going to put it in here for you guys, but I have a feeling that if I asked you guys if you believed me or not, you probably just would. So if you're one of those people that is super interested in how formulas come to be, there is a proof in the book on page 494, so rather than me doing it for everyone and lengthening the video, I will just assume that if you're interested, you will look there. But this is the important part. This is the formula right here. So we're going to do one practice problem right here. So express log base 5 of 140 in terms of common logs. So what we would do is you would take the common log of this number first, because you're using n first in this formula. So common log of 140, and then over the common log of 5, which is the base. So it's the common log of the input minus or over the common log of the base. That's how that formula works. So we're going to plug this into our calculator, and like I said, I realize that our calculator can just do this directly, but I want you guys to know this formula. So we will set up a fraction, and I'm going to do log of 140. Remember, if you skip the base, it assumes it's 10, which is what we want, over the log of 5. Okay, so we got 3 and this would be 0704 if we're rounding to the 10 thousandths place. So we've got 3.0704. So remember, this is now the base on 5 that would give us an answer of 140. So just to show you how close we got, if you take 5 and raise it to the power of 3.0704, we should get just about 140, which we do. Of course, this is an approximation, so this is going to be just slightly off. All right, that's 7/6.